Okay, good morning. We just got a midterm exam last Tuesday. So I think based on the initial looking, most of students did quite well. Okay, so you should not worry about it. I will discuss with TA on the detailed grading, and everything should be taken care. Okay, probably will take one more week. We finish all the grading, then I can distribute the homework back to you. Okay. So for you probably can see the coming deadline is the first assignment. The assignment contains some programming part. Okay, the weight basically, if you click this assignment, we did not put down the concrete weight, but in Piazza, people actually ask about the weight. Actually, each question is written question, like question 1, 2, 3. Each one worth 20 points. Simply says each sub-question is 10 points. And the last question worth 40 points. It simply says, because this one takes a longer time, takes more effort to do it, we just put a little more weights. That means this one double weight than the other one. Okay, so that's about the weighting. And there are some students asking about whether his answer is right or wrong. Okay, I think of course you can check with your friends to see whether the result you got is too strange or it's. I think the passing one should be somewhat close to what we show on the slides, okay, because the data is not exactly the same, but somewhat similar, because when Izhou did her experiments, that's the one just published, some new paper not got in yet. So now you got a complete set of the data sets. It's a little different, even we say that's the same year data set. So they have slight difference. So your answer to the one you compare with the slides, it has somewhat difference, but it should be basically the same. Okay, should be largely the same for like a passing. What's the result you can get? You can check on the slides to see whether the results is somewhat close. If it's too far away, you probably want to check whether your coding has any problem. I have asked the TAs to pay more attention these several days, because these by Sunday night is a due date. Likely TA may set up some additional extra office hours on Friday. Okay, so if you really have questions, you try to go to his or her office hours. Okay, then weekend, if you really have some question, you can put on the Piazza. Either TA may answer you or some other student may help you. But I hope everybody can hand in the assignment on time. Okay. So this is about the homework assignment. Okay. I think it's interesting, but it takes some effort. Okay. Now we get into the new session on text mining. So last time we said we originally wanted to do the text mining before the midterm, but we got lots of things to cover on the network part. That's why once we get into this text mining, it will take the remaining part of the semester, some substantial part. Okay. So the text mining, I also partition them into two parts. The first part is on phrase mining and entity typing. Okay. This is the waterfall. You probably see this is a huge waterfall. It's in Brazil and Argentina, the border, called Iguazu Falls. It's the largest fall in the world. Okay. For the single one, it may not just one fall. It may not be as big as Niagara Falls. But there are so many. They have, almost the whole area just filled up with falls. Okay, so The first one is very similar to what we discussed about our whole philosophy on turning data to knowledge. And we said, if we want to turn data to knowledge, and we know the network is very powerful. You already saw in the first part, you did a review before the midterm. You can do a lot of things using structured networks. You can do prediction, you can do clustering, you can do similarity search. It is very powerful. But the problem is the real world, okay, they are not in such nice structured networks like a DBRP or YERP or those kind of networks, because those networks were somehow created by human efforts. Just thinking about it, DBRP, you got so many different papers, conference. It is, those conference organizers getting this. These are the authors, these are the titles, these are the venues and the publication dates. They put them in a structured format. Then they send it to PubMed or DBRP. That's why you can get it. Okay. But if you check the real world, for example, newspapers, or you check even the normal YERP without much structuring, there are lots of comments, and you check tweets, you check the detailed contents in the research publications. Like you get many sessions of those papers, you check the paper contents, they are not structured. Okay. That means the real world data is unstructured. Many could be text, multimedia, social media, those kind of data sets. But we want to turn these unstructured text data finally into knowledge, how we do it. Okay. So actually, if you can see, the major idea is, the first, we want to structure them. You give me the text data, which is not structured, but we want somehow develop, powerful methods to structure them. So the first one is structuring. That means we want to transform unstructured data into structured typed, entities and relationships. Okay. That's one, actually, it's the one we're going to discuss in this session. Okay. It's how to structure data, getting phrases, get types. Okay. Then the second one is networking. That means you take those structures, you construct it, good, informative, the right schema, you get the right structure, you construct the structured networks. Then with these networks, we can do mining, we can do reasoning. That part, actually, we have discussed in the first part on the network, how to mine heterogeneous information networks. So that means we actually, in the first part of our course, we discussed this part, mining, reasoning. Okay. But the second part, where we are handling more challenging task, which is how to make the unstructured data to become structured. Okay. Then if we think about it, the whole game, we want to turn massive unstructured data into structured knowledge. Then the game becomes, data to network. That means you first do structuring, do networking. Then from the network, you can get knowledge. That's a mining part. Of course, this is a data mining course. We actually, even for data to network, we are not get this done by human. Okay, it's too expensive. We are developing new methods automatically turn these unstructured data into structured networks. Okay, that's the whole game. Okay. If you really look at the picture, that's a picture actually worked out by our TA, Fang Bo. He wrote his thesis proposal. He drew this picture. I quite like the picture. I actually just did a minor modification. It is a picture we are using to give you the whole framework. Okay. You can see we got text corpus, newspapers, tweets, social media, all things here. Okay. And we usually may have a general knowledge base, like a Wikipedia or Freebase or DBpedia, some, Yago. There are lots of people created some general knowledge base. Okay. Then we take this general knowledge base plus our unstructured corpus. We want to extract keywords and phrases, and we want to construct the types. That means, whether, say, Ronald Trump is a politician or is a businessman, or in reality video, it could be an actor, right? So what is he in this case? Whether we can automatically identify it. This is that type, okay? Then from the phrase and type, we may be able to construct, heterogeneous networks, and from heterogeneous networks, we can get knowledge, okay? You can see before the midterm exam, we basically are discussing this arrow, right? We say, we give you a network, heterogeneous network. How could you get knowledge? Okay. That's this game. Now, in the second part of the course, we are more discussing this part. Okay. Because this part is more challenging. You get unstructured data. You don't want a human get involved, but you want to turn them into structured knowledge. This is more challenging. Okay. You probably can see the 4. I took a picture from the other angle. You can see the 4 is really big, right? And actually it's much bigger. I only took a small corner. Now, let's look at the first one we call phrase mining. Okay. The motivation to some extent is very obvious. Okay. For any language, not just English, any language, there are many things getting together to represent a whole concept. Okay. Just give you a simple example. Suppose if I give you a word, say united, okay, you actually do not even know what I mean. Because if I go to an airport, I say united, you probably say, oh, that's United Airlines. There's no question. But if I go to United Nations, I say united, actually you really do not know what I mean, because there's a United Kingdom or United States, United Nations, or United Arab Emirates. There are many united. Actually, I went to even Brazil. The guide actually told me Brazil in the past called United States of Brazil. Okay, so that's another United. That's another United, right? So let's look at. We know unigram is ambiguous. But once you get into phrases, for example, if you say United Airlines, United States, that's no ambiguous. You exactly know what you mean. So we call the phrases as minimal semantically meaningful unit. It simply says, you mine the phrases. What is a phrase? The phrase, if you decompose them, you lose the real meaning. Okay, you get them together, you get one entity you recognize. That's a phrase. For example, you say University of Illinois. Okay, that's a phrase. Then people know it. Even you say University of Illinois at Urbana-Champaign, it's a phrase. It's longer, but it's one unit meaning. But in the middle, you just say Illinois. Actually, you distort it. This is a university. It's not a whole state. You just pull Illinois out. It does not really make sense, right? So to that extent, we say we want to get a phrase. Then when we analyze the sentences or analyze the whole document, we will not distort the original meaning. That means we are analyzing text from the word granularity, we go up to phrase granularity. This is much, much easier. Okay. Actually, people in many cases, they say, oh, natural language study is really hard because people have many, many interpretations. But actually, why human never get confused? Because a human can recognize what is a meaningful unit. Okay. I remember when I took a natural language processing class, the professor actually, first time they give you a typical classical example, say, time flies like an arrow. Okay, so this is very confusing. If you talk to any human, they won't feel it's confusing. Time flies like an arrow. You just say time flies really fast. But if you parse, you say time flies, okay, it's one unit, one phrase. So there could be dragonfly, but there also could be time flies, okay. Then you say this like means love. It means the time flies love the arrow, okay. So you can parse in that way, okay. But actually, if you really do this phrase mining, you'll find it will never pass away. Because how many times you see time flies. You see dragonflies, you see all kinds of flies. But you go through the whole corpus, there's no time flies. Right? So you won't pass that way, so you will not get that interpretation. Right? So we actually, this phrase mining exactly follow this. You are not just watch one sentence. You'll watch the whole corpus. Then you will make the right decision. You will never say time flies is a phrase because you won't see it in other cases. Right? So we will see how we do it. Okay. Of course, we should say there are many, many people in the past try to do phrase mining. That means that they really want to grab the phrase out. There are many previous studies. The most typical one in natural language community called chunking. Chunking means you get a phrase, you get several phrases, you try to get a chunk. So this one is a phrase. Okay. But chunking, sometimes what they do is they say, oh, you can get a, this is noun phrase, then you have, beginning of the noun phrase, intermediate one, and you get another one, you get a beginning to the end, so you get a chunk. Okay. So that's a typical NLP people doing. But there's one important thing you probably can watch out is for many, many NLP people doing this name phrase, chunking, they need training data. Simply says, you have to give me examples. How many examples you need to give? Sometimes quite a lot. Just give you a simple example, okay? I talked to some NLP professors. They just told me, if you want to do good mining, for example, for 2013 New York Times articles. Remember, even 2013, the New York Times, actually, there are so many articles. It's in the order of million. Okay, that's a lot of articles. What you need to do is you pick up the typical 500 documents. You give it to the NLP people or to the domain experts. You ask them carefully label everything. Okay, that's 500 documents. Of course, it may take even days, right, to do this. Expensive. Then you can do the remaining in a reasonable quality. But the problem is, I just ask the professor, say, whether you label 2013, I can use it for 2015 New York Times. The answer is no. You just cannot use it. Because the news 2013, you go down to 2015, it changes quite a lot. Okay? Your previous label, actually, to some extent, you may not even see the case in 2015. And 2015, you did not label them. So you get lots of mistakes. It doesn't mean it doesn't work at all, but you get many more mistakes. It's not, reaching the acceptable, quality. That's a lot of trouble because, how many people want to keep doing those labels? It's very expensive. Plus, there are so many people writing unstructured one, like tweets, or people writing, the domain experts writing medical articles, computer science articles. You go down to different fields, you hire people to do 500 documents labeling. It is not a very economic, at least. So there must be some way whether we can do something unsupervised or barely supervised. It means a very minimal thing, you can get it done. Okay. So that means the thing we want to do is we want to do something more automatically. Okay. There are some people recently do this, say, using some distribution feature based on the web n-gram. Okay. I do not know whether you heard some Google discussion. Okay. Google said why the big data is important. They actually tried it. They tried to take almost the whole Google corpus, doing some kind of NLP processing. They say their results, their performance is comparable or sometimes better than you do substantial labeling or very deep processing methods. Why? Because the data is huge. They disclose patterns. That means the big data is not just the words. They have the real use. From the big data, you get statistics. The statistics may help you disambiguate many things. Okay. Actually, quite often, even the students sometimes will give me an article give me their own article, ask me to check. I sometimes I say this one should be capitalized, this one should be writing this way. The students start arguing with me, say, no, you are wrong. I write this way. I feel it's more right. But I just say, it's very easy. We don't have to argue. You Google it, right? You Google it. You just look at it. If they put it a capital, they write this way. That's a standard. Okay. Most time, actually, if I'm not sure, I'll try to blame the student. I first Google it to make sure it's right. I forward a student an email or say you should write the other way. Okay. So that's the reason the big data does help. Okay. You actually can see if you use annotation and training, you can get some good performance, okay, on the F score. But the major problem is you have very high annotation cost, okay? And if you get a new language, you get a new domain or genre, or even New York Times, you get 2015, you jump to 2013, it may not work anymore. Okay? So what we really want is more automated methods. Okay? That means we have to jump out and think whether there's a better way to do it. Okay. Now we look at, there are lots of new methods we want to examine, and that means whether we want to get a phrase out in a very, very, automated and powerful way. We actually check many papers. We give you somehow like 3 classes of methods. I believe everybody heard or somehow know topic modeling. Okay. Topic modeling was developed in, I probably cannot say it's one person, but quite influential ones could be like David Bly and Michael Jordan. David Bly did PhD. You probably saw it by my previous slides on the advisor finding. David Bly got a PhD in Berkeley, following Michael Jordan, and he became a professor in Princeton. He also worked closely with like CMU professor, John Lafferty. They actually developed quite an interesting method called topic modeling. Topic modeling basically is you got a corpus of documents. You assume there's a generative model. The words are not in this document are not coming out automatically. Is there some hidden generative mechanism generating those distributions? So you can partition this into different topics. Okay, so you give me an N. Okay, N could be 100 or 30. I give you 100 documents, or you can say 100 clusters. Each one inside is a single word, but you get a ranked list of single words. You get topics. Okay. For example, you say deep learning. You may have other things like neural networks or something. They all partition into one part. That's a topic. Okay. So actually, to get phrases, lots of people are thinking about these topics because topic already take the meaning somehow, put things together. Okay. Then, for example, if you get a machine learning, machine and learning in the same topic, likely you may get machine learning together as a phrase, right? So can we do this, or whether it's really good? Okay, we are, looking at those different previous studies, then we'll see what is the best way we can get the topic. Okay. So the first thing is, people can think about it using unigram, you can get something, okay? But for example, this one is something got from the topic model, okay? The topic modeling, you may be able to get a learning, reinforcement, support vector, machine vector, or something like this, okay? Then you may be able to combine them into a bigger one, right? People, for person, if you read this, you say, oh, this must be machine learning topic, because machine learning contains many, many subtopics, like reinforcement learning, support vector machine, feature selection, random forest, or something. You can get this. But if you read this versus you read this one, This one actually give you like a support vector machine is one phrase. Reinforcement learning is another phrase. Conditional random fields is another phrase. This will make much more sense, right? Because you actually know the minimal semantic units like feature selection, conditional random fields. Those are, much better rather than you pick a random out as one single one, because random can actually fit into many, many topics, not just machine learning, right? So we know this. We want to get this phrase like this one automatically. Then we see previously how people are doing it. Okay. Actually, there are several methods. I basically say there are three major methodologies we can see. One is you generate back of words, then generate sequence of tokens. What do you mean this is, just to give you a simple example, the first one, Wallach, and in 2006, he got a paper called a bigram topic model. What is bigram? That means you give me a sentence. Okay. I take this sentence, I chop every two potentially to be a phrase, right? You give me a sentence, I chop every two. Okay, no matter whether meaningful or not, I do not know. But I take every consecutive one, I chop them out. I have many, many bigrams. You consider single word is unigram. Then the two words getting together is bigram. You get many, many bigrams. And in the meantime, you do topic model. Okay. Then those bigram, some strange boundary, you put them together. It should not be a good bigram. In the topic modeling, they will be ranked really low because it's very rare to see such things. So they will be ranked very low. They will fail out. So in the topic model, you are going to get something reasonably meaningful. Okay. So this is the bigram model. Okay. Then some people actually go even further to get a topical n-gram model. Okay. N-gram model means instead of you chop every two, you chop it 2, 3, 4, you chop many such longer ones. N means it could be 3 or 4, even longer. You get longer ones. Then you chop them, you throw them into topic model. You may generate some longer phrases. Okay. But you probably know this is pretty expensive. You think about this. I probably can show you this bigram. Okay. You can see the bigram model, what it did is using probability generative model, the conditions on previous word and topic when join the next word. That means you actually looking this word and looking the probability to get next word. Then you, based on this, you generate the topic model. But you can expect bigram and topical n-gram, they are very expensive because they not only check single word, they check all the 2s or 3s. So you check much more, you generate. Actually, even LDA, just using single word, it is pretty expensive one. Okay. Then you get into bigram, n-gram, you can think about it. It will take much longer time. And another thing is, not only they are very slow, but also they have high model complexity. That means sometimes you see there are 2 or 3 things getting together. It happens to be together a little more. Then you generate this phrase. Actually, this one may not be a phrase at all. Okay. For example, you say, the paper says, or the paper claims, or something. You go to a few papers, they really say the paper says, or the paper concludes. It's not a really phrase, right? You think about this is, somehow they may generate something tend to overfit. Just based on your current corpus, you said a few times, they generate something actually may not be a phrase. Of course, those things, if you do a little, parsing or something, you probably can get rid of something. Okay, so that means you use part of the speech, integrate with this one, you can improve the model. Okay, so these are several previous studies trying to say, I grab something, in the meantime, I feed this into topic model to generate the new topics. Okay? but it may not work that well. It's very expensive. Okay. But it's still, you can see, you still generate something meaningful. If you look at the results, people can see. For example, this topic is about reinforcement learning. And then you see this is LDA generated single word. You get these state, learning, policy, action, reinforcement. You get something. If you are right in the field, you read it, you probably can figure out this one is about reinforcement learning. But you look at, you know, the n-gram, you get this n-gram model is 2 and more. Okay, you can see this is just using LDA. This one is using bigram, n-gram model. Even they generate just a unigram. That means even using this model you feed into LDA, you generate this unigram, this one, already better than this part. You look at these two columns. This one, the quality actually is better than this. But the n-gram model, like you get a 2 or 3, it makes much more sense. Right? If you just read it, as a domain expert, you read it, you probably say this one makes a lot of sense. So it is successful to the extent that you can see you get some meaningful phrases. But the price you need to pay is rather costly. And also, the model is quite complex, and you may have some overfitting problems. Then, in the meantime, there are studies. Okay, this is another example. If you can see, this is speech recognition. This is the 2 to 3 grams. This is the n equals 1 generate this. But this actually still could be better than just purely using LDA. Okay. But people may say this is rather expensive. Okay. Then there are other proposals. Okay. One proposal actually was done by David Bly and John Lafferty. Okay. Like we just remember David Bly as the one who actually did this LDA, this topic model, become very famous. He's very young, actually. And his postdoc advisor, John Lafferty, actually was Professor Zhai's advisor as well. Okay, Professor Zhai also got a PhD from John Lafferty. But John Lafferty now is not in CMU. He's in University of Chicago Statistics Department. Actually, I think a few years ago we invited him to come here to give a talk. Okay. And they too actually work out one called turbo topic. They also want to get a phrase. How they get a phrase is they first do LDA, do the topic modeling, generative model. Okay. After they generate this one into each topic, for example, you got a learning, you get reinforcement, all these things all in the same topic. What you do is this time you start combining them. Okay. The turbo atomic is you first perform latent dictionary allocation on those corpus, and then get all these tokens to give the topic. Then what you do is you merge the adjacent ones. You say, oh, you say reinforcement is topic number, say, 50. Learning is also topic number 50. They are together. You say, oh, reinforcement learning is a good phrase. You grab those phrases out. Okay, that's a trick. Okay. Then I probably, before I go down there, I show you the real example on turbo topic. Turbo topic, that's actually from their paper. If you really go down there, this one actually generated the numbers. All these is from the same paper. Okay, we did not change it. Something you can get it. For example, phrase, transition, they are all topic 11. Okay, you get phrase transition. That's nice. And you get, for example, let's see. There, phrase diagram actually is also topic 11. You get a phrase diagram. Okay, and you even got a quantum phrase transition as a phrase. You grab them out. That's nice. Okay, but there are problems. If you watch it, you may find the problems. What's the problem? You just look at something. Okay, for example, you may have a general theory. General theory looks like a good phrase. But general is in topic 11, theory is in topic 127. They're not even in the same topic model. They are together. Unfortunately, they cannot match. Right? So you will not get anything like a general theory. Of course, you may not be able to get it. There are many other things, like a modern definition, or you have, the symmetric group. There are many some things like spontaneous results or topological phrase transition theory. You will not get them together, right? Because they all belong to different models. And just to give you a very typical example, you think support vector machine should be in the same topic. But if you get a large corpus, you just think about this, okay? The vector can be anything. Vector likely could be in linear algebra, in even math or physics. They have lots of vectors, right? The machine could be even more radical. Machine could be in mechanical engineering, right? They have so many machines. So the support is even worse, because support, you go to like Obama or Trump, you have how much support. It could be politics. So if this supports vector machine separate into 3 very different topics, there's no way you can combine them, say it belongs to machine learning. Right? So you probably can see that's very likely the case. Okay. So if we do this turbo topic, you will miss lots of valuable things. Not only they are expensive because you have the first 2 RDA, then you try to power them up, you actually miss lots of valuable phrases, right? Just because they put into different topics. Okay. So there are problems. Then I got a student called Maria Danilevsky. Okay. She did a PhD with me. Now she's in their natural language machine learning group in IBM Armored Research Center. She worked together with Shi Wang. They two actually generated a method called CURT. Okay. What they do is this. They say, instead of thinking, latent deletion allocation, you try to generate something. What they say is you first do latent deletion allocation, but in the meantime, you do post-processing doing frequent pattern mining. Okay. That means instead of here, they just try to pairwise them. Okay. But Marina's approach essentially is going to do this frequent pattern mining on every topic. Okay. That means you get every topic, you try to find the patterns. Okay. And based on this pattern, you rank the phrases. You generate something better. Okay. So, and she actually shows, comparing to turbo topic, comparing to many other methods, she can generate better ones. Okay. That's what she did. You can see Marina, what she did is she got like this one is machine learning topics. But unfortunately, you probably can see there are many things using a good phrases. They are in different topics. Okay. Just give you a simple example. You just look at this. Knowledge discovery. Okay. And we know KDD, or knowledge discovery from data. Knowledge discovery is a phrase. But unfortunately, knowledge discovery, you probably can see this point, they are partitioned into different topics. If they are in different topics, there's no way, even you do frequent pattern mining, you will not be able to recover this partition. Because you do RDA first, you already partition them into different piles. Okay. And you're not looking for cross-pair, try to generate phrases. Okay. So like this knowledge discovery, you'll never get it. Okay. And there are many other things like this actionable knowledge, even sometimes least square could be partitioned or something. So there are lots of things may or may not be very good. Okay. So, but they work out some good way to judge what is good phrase. Okay. They work out a good way is this. They work out 4 ways to judge the quality of the phrases. And that's very valuable for standards. And even later, we got a student later, after Marina's thesis, we got a few students jump in. They got something much better, okay? But these 4 standards she developed is still valuable, okay? What are the 4 standards? One called popularity. That means if you look at the whole corpus, the quality space, quality phrases, usually they are very popular. Just give you an example. If you look at information retrieval versus, say, cross-language information retrieval in a corpus, you probably can imagine the information retrieval will be much more frequent than cross-language information retrieval, right? Because cross-language means, you know, you give one in English, you go down to, say, French, you try to find some information, right? That means cross-language information retrieval. So information retrieval should be ranked higher because it's more popular. That's based on the popularity or frequency, you can get it. The second one, called discriminativeness, simply says you got a topic. Suppose this topic is machine learning, okay? Then you got another topic. Suppose that topic is database systems. Okay. So what is a good phrase for machine learning one? Discriminativeness means you may find certain phrases, they occur more frequent in machine learning, but occur much less frequent in database systems. Then that's a good phrase. You put it in machine learning. For example, you make a support vector machine in machine learning, but you won't get support vector machine in database. They may have some words, but very few, right? But if you work out one, say, scalability or high efficiency or performance evaluation, probably, you know, the machine learning and the database, they are discussing this. That's not a very, you know, very discriminative in machine learning, so you won't rank very high, okay? The third one called concordance. Concordance means, okay, means they really naturally, concordance means they naturally harmonically getting together, okay? Just give you a simple example. If you see active learning or reinforcement learning, they actively getting together, you know, very, very popularly. But if you look at learning classification, okay, even they occur in many documents, they may occur frequent, but they may not be frequent together, right? Like learning classification looks very odd because classification is one kind of a learning, but they don't really combine together, okay, that are frequent. A typical example could be like a strong T, okay, then powerful computer. People never say strong computer, powerful T, right? So they say strong T, I want to get strong T. That simply say even strong and powerful may mean something quite similar, but strong T, you know, getting together is much more natural. There's much more concordance. You never say strong computer, right? So you may say powerful computer, you know, high performance computer, yes. Okay. What's the difference between popularity and concordance? Okay, that's a good question. Concordance means, actually, in Marina's, the example is this, okay. Both learning and classification may be very popular, okay. I mean, learning, classification, they are very popular, but they do not getting together so popular, okay. That means individually you look at learning and classification, they are very, very frequent, okay. But they just do not pair up like a phrase, okay. So that means if you just based on popularity, you may put a learning classification there as a popularity, okay, because they do appear, you know, very frequent. Even you go to machine learning, you may see these words in the same document or sometimes in a longer same paragraph or same long phrase. They may happen together, okay. But they really do not form a phrase. Simply says, putting these two really together one after another is very, very rare. It's not really look like a phrase, okay, to that extent. So this learning classification, they are popular, but they are not concordant, okay. You probably can see that. Another one is completeness. Completeness means you see vector machine, you see support vector machine. Then you may go down to those machine learning, topics. You look at it. Almost every time you see vector machine, they have support vector machine as well. Okay? So that means vector machine itself is not complete. You put a support vector machine, it's a complete phrase. The reason is you check these two, you may find if this one happens 1,000 times, this one happened to say 1,002 times. Probably you will say support vector machine is a real one. This one actually is a faked one. It's not a, it just occasionally happen. Remember, this is corpus dependent. Okay? Corpus dependent means if you go down to, say, mechanical engineering literature corpus, they may really have vector machine there. They may have a vector machine much more popular than support vector machine. In that case, the vector machine is independent. It's a good phrase. Okay? But you go to machine learning or statistics, you will find support vector machine. You won't find vector machine that popular independently. Okay? That means you have to go back to see whether this is independent or not independent. Okay? That one later we are going to discuss how to do this. Okay? But these are the four principles. Marina actually used this to guard against the quality of the phrase. She got very good phrases. And if you read her thesis, you can download from the web, from the university. You may find it. She did a lot of studies, not only just for computer science. She picked up those novels, journals, their newspapers, many things, shows the phrase she found actually is a very, very high quality phrases. Then you probably can see she actually got 1, 2, 3, 4, 5. The last one is she used all the 4 standards. Then the others, remember these 4 standards, the others is each one is knock one out. That means I don't care concordance, what I will generate. I don't care discriminating this, what I will get. I don't care popularity. No. She knocked out each one, use the same parameter. She generated, you can see. That's the last result she generated for machine learning. And these are the other people, she knocked out one standard generated. You clearly see, you knock out one standard generated, something is not so good comparing to this one. Of course, it doesn't mean, like you knock down the discriminant, overall it's not that bad, you probably can see. But the others, you generate something really not very good. But this one you generate really look like almost a human generated, right? It's very high quality. I mean, the ranked one. For example, you may say, oh, constraint satisfaction, it generates not bad. It's not bad, but it's not ranked that high. According to her standard. She has other things ranked high. Just give you an example, like this support vector machine ranked high, learning ranked high, and this one actually has no learning. And there are many things. You actually can read her thesis. It generate many examples. It generate very high quality one using these 4 standards. That's the previous study. This one, you probably can see, that's the waterfall. This one actually is huge, but it's right in the middle of those waterfall. The waterfall is really, really huge. And many, many layers you probably can see. It's really big. And the trees, you can see those trees are so small. Okay, it's really big. Now we give you 2 new algorithms, both published in 2015. If you look at Marina's one was published 2014, okay, in Simon Data Mining Conference. But these 2 were published, like TopMine published last September in VRDB conference. Actually was accepted in 2014 in late time. It missed the conference, 2014 conference already. They put into 2015. After that, segphrase actually is a new algorithm we generated. It's a very strong algorithm, and published in Sigma 2015, and got a YERP Dataset Challenge 2015 grand prize. They simply say YERP was so impressed. This paper published within a month, they give a grand prize. That simply said. Of course, they are using it. Last December, I actually got a trip advisor send me email say they are developing multiple languages using this method. They want to collaborate with us. Simply says this is not only in academia, in industry, they really like this method. They see its efficiency, the high quality, without anybody supervision. So it's very strong. Okay. Then we look at Ahmed Erkishki's paper. He worked out a new method called top mine. Okay. Top mine actually is the topical phrase mining. Okay. That's why I call it top mine. The top mine, different from Marina's CURT approach, is Marina's approach is first do topic modeling, then do phrase mining, follow the similar methodology of turbo topic. Turbo topic is Bly and Lafferty. They work out turbo topic in 2012. Okay. So 2014, Marina actually, the major thing did is instead of getting each topic, try to go back to do that. They do frequent pattern mining. Then they use 4 criteria to judge it. They find better phrases. But Erkishki, what he found out was first doing topic model could be fatal. The reason we already seen, you get like a knowledge discovery or a support vector or something. If the very beginning you partition them into different topics, you're out of luck. They never be able to combine them together. Those phrases, you constantly miss them. Okay. So, and he says, why we have to do this way? Why we cannot reverse the order? We first do phrase mining. Then we take those phrases, we do topic modeling. Whether that will change the game. Okay. Actually, she was doing something similar to Marina's approach, but change the order. Okay, because I originally actually asked him, say, Marina got a very good one. You just do this because he knows a little Arabic. He was born in Egypt. He grew up in the U.S., but he still knows Arabic. We work with Army Research Lab. They really want to see whether we can do Arabic phrase mining. Arabic has many dialects. So he knows one, which is used in Egypt. Okay. He says, I can try. Okay. Then he worked this out. He said, there are always some very good phrases missing. I could not use this method. And then he think about it, why we cannot first do frequent pattern mining on the words itself without thinking about topic model. Okay. After we getting those phrases, then we feed into topic model. We may do something better. And he tried it. It's amazingly good. Okay. So what he did is first perform frequent contiguous pattern mining to extract the candidate phrases and their counts. Then what he did is he goes back to the document to segment the document. That means he will say, this phrase may be a faked one. I could go back, even their count is 1,000, maybe they are all faked. Okay. And how do you know they are all faked? Just give you a simple example. Okay, support vector and support vector machine. Maybe support vector got a 1,000 count. Support vector machine also get a 1,000 count. Which one is faked? The support vector is faked because every time the support vector comes, the support vector machine comes. How do you do it? You go back, give the credit first to the longest one. Okay. If the longest one take it, they say, I got this support vector machine, that's mine. The support vector get no meal, okay, get no count. So you keep decreasing. Finally, the support vector, if there's no, any time you get support vector, of course, a support vector, if you really go down to support vector machine, you will find support vector, they do have it, okay? But support vector machine has more. But a support vector, you get suppose you get a 1,500. And finally, your real count maybe just 500. The 100 actually credit to support vector machine. Okay? So in that way, he got a real count. Okay? And after this, he actually part up them into bag of phrases, feed them into a revised LDA called phrase LDA. Then he got a really, really good results. Okay, let's look at this, what he got. His first argument is saying, you look at this, suppose, of course, he give an example, he just try to argue his method is best. He colored this, say, knowledge discovery, suppose if you first do LDA, knowledge discovery in different topics. Support vector machine, the vector is different from support machine. Then you are out of luck. You will never be able to find knowledge discovery. You will never be able to find support vector machine or even support vector. Okay. So what we want to do, what he wants to do is first do this phrase mining, then do topic modeling. Okay. He used a very straightforward, simple statistics, and it works so beautifully. I just show you this one slide. You probably can see the trick he played, and it's very simple, very fast, and very effective. Okay. Why? You look at this. Okay. You give it a simple example. Suppose you find in DBRP, you find a research paper. The title is Markov Blanket Feature Selection for Support Vector Machines. You look at this. Of course, you know, when I read it, I know the meaning. That's why I say Markov blanket, then feature selection, and for support vector machine, because I know semantics. If you ask a guy who does not know anything about computer science, he could read something, you would laugh, right? Because it doesn't make sense if you pair up in some strange way. Okay. Actually, that's exactly human is doing phrase mining. You know, you even do not know, but you do phrase mining. Okay. So what he did is very simple. He says, I cannot just look at this single title. It doesn't make sense. But I have so many titles. I have 2 million titles, right, in DBRP. I look at these 2 million titles. I just need to go through, do the frequent pattern mining. That's it. And his frequent pattern mining is different from Marina's. He only look at the consecutive one. That means he will not look at a gap. Marina's argument is sometimes a gap is useful. Just give you a simple example. She says frequent pattern mining, you have mining frequent patterns. You have frequent pattern mining. You have mining closed frequent pattern. You may have mining sequential frequent pattern or mining top K frequent pattern. They are all mining frequent pattern or frequent pattern mining. That's why the order and the gap I can tolerate. And finally, I find a very high count for frequent pattern mining, okay, which is true. But in many cases, you also team up something unexpected. Because you allow the gap, you allow changing the order, you generate something may not be always good. Okay. Then his argument is, since my corpus is large, I always can, without thinking about those kind of combinations, I actually get a good patterns already. If you need that, I can do post-processing, merge them. Okay. But how he did it, it's just not just checking the count. Actually, it's checking the correlation using z-score, okay, or correlation score. Anybody remember z-score, correlation score? Okay. Z-score actually is this. Just to give you a simple example, even you do not quite know it. Okay. But I assume everybody knows the standard deviation, right? If you do not know standard deviation, I will have a real hard time to explain this. Okay, I assume everybody knows. At least when you play the dice, okay, normally if you flip the coin, normally the head and tail should have reasonably equal. If you flip many rounds, the flip you will have a reasonably equal in the middle if your coin is not loaded. Okay, it's not tilted to something. So we assume, okay, things you get a Gaussian distribution or standard deviation. You get a standard, distribution, Gaussian distribution like this. People call bear curve, whatever. Okay. The most important thing is the majority things fall right within, say, +1, -1 sigma, +1, -1 standard deviation. That one if you add them together, this is 68%. That's within 1 standard deviation way. Within 2 standard deviation way, you get much more. You can see you add these two. So within 3 standard deviation way, you actually got a 99.7. That means if you find something 3 standard deviation outside, the chance to be that far is only 0.3%. Okay. So when you want to check phrase, it's very easy. We just take support vector together. Okay. You look at how frequent the support is, how frequent the vector is. Okay. Just give you a simple example. Suppose you find support, the frequency is 1/1,000 in your document. Okay. The vector is 1/1,000 in the document. If these two are not phrases, they get together, a chance is 0.1% times 0.1%, you get a 1/1,000,000. That means actually within your 2 million documents, you may find support vector, these things come together only twice, right? But if you check your titles, you find support vector get together is much more than twice. Maybe you get 200 times. Okay, what happened? That's quite a lot of standard deviation away, right? So he actually used something not exactly z-score, but is very close, called alpha score, which actually is called significance score developed by Church, by George Church, who is a very famous bioinformatician in Harvard University, leading a very big lab. Okay. But this significance score, not just for bioinformatics, actually it's for this one equally well. You can assume this one, your understanding is just a z-score, because it's very close to z-score, if you really check the z-score. What you can think about is this. Okay. Support vector machine getting together, you check the corpus, this one is about 12 standard deviation away. How do you explain this? Okay. You probably know that, like last time they said in Iowa caucus, the caucus, the Sanders and the Hillary, they got tied in that particular caucus. They flipped the coin. They said it's really lucky. There are 6 times they flipped the coin. They all go to Hillary. That's why Hillary actually win the caucus in a not big margin, but they did win in Iowa, right? So that's very odd. 6 times you flip the coin, they all go to Hillary. But this is much more odder, because you can see that that's 12. That simply says it's almost impossible. They must be a phrase, right? Think about why they get together. It simply says people want them to be together. They use together. That's why it's a phrase. Okay? So with such a simple judgment, remember this z-score is very easy to compute. Right? You just these several counts, you add them together, you calculate standard deviation, that's it. Right? And then even you glue support vector as one word, you try to see machine whether it should be there. Okay, you will find support vector glue machine, you still get a standard deviation way. That means they are a phrase. Okay, don't be fooled. They really get together because people want them to be together. They are phrase. Okay. Now we get into the more interesting part. Okay, you look at this. That's what Ahmed is pretty smart in a way. He really see the real habits, the potential problems. Is this? You look at the feature selection and selection for. Okay, you probably know by common sense. Selection for is actually quite frequent. Think of selection for, you go down to DBRP, you check the phrases. Selection for is not that unpopular. But feature selection, if you check it, it is more popular. Okay? So now feature selection and selection for becomes rivals. Because one guy said, oh, feature selection I found is a phrase. The other guy said, no, selection for actually is a phrase. Okay. Then how we do it? We fight. That means which one has even bigger standard deviation away. Okay? The z-score is bigger. If feature selection is bigger, that's feature selection. That's the game. Winner takes all. Okay? Once you say feature selection is a phrase, the selection for get no meals because they lose. Okay? And when the selection for you will really credit them is you find feature selection for getting together. That's the getting together is also very frequent. You may say feature selection for is a phrase, is a larger phrase. Otherwise, in this one, I don't say other places you win or lose. In this one, because this group can only go to one, cannot go to both. Okay? It's more like you get a vote. You vote Hillary, you cannot vote for Bernie. You only have one vote. Okay? So that's the same thing. Okay? So in this case, you vote feature selection. Okay? That's it. Okay? That means if somebody counts selection for, and this for this particular title, you have a decrement by 1 because you miscounted, right? So that's, you have a raw frequency, you have a true frequency. That's exactly, we call this one is document segmentation. That means you go to document and really segment them, you see what is a real game. Okay, you credit to selection for, to feature selection. That's why after you do this game, this title, immediately you read it right. You'll say Markov blanket is one phrase. Feature selection is another phrase. Support vector is a hidden one, but the support vector machine is a bigger phrase. Is that clear? Okay. So that's the game he played all over before even feeding to any topic model. And he got amazing results. Okay. Of course, he also discussed other potential, because he used the significance score. He basically says you almost can use anything. I don't care. You use anything, you always get a very good results. Just use this philosophy. Okay. You can see he actually tried something like a PMI or a significance score, a t-test, a z-test, a chi-square, likelihood ratio. You can use anything. It's nothing magic for his alpha score. Okay. Just to say the principle is you first try to find those consecutive ones as potential phrases, candidates. Then use those 4 standards. You can judge them. Then you can feed them into topic model. Then you win. Okay. So that's, and his topic model now is a little subtle because originally the topic model just words. Okay, that's LDA, just using words. And he doesn't want to completely say you only can see phrase, you cannot see word anymore. Okay, he actually got a one is you get words. In the meantime, if these words has a high chance to build a phrase, then he built a bridge. That means these words actually somehow are connected. And using this model, he just called this one is a phrase LDA, or constrained topic model. Then he ran his one. He got a very, very good results. You see, the first thing I should say is, if you look at the time spent, is amazingly fast. The reason is that his phrase mining is just a simple counting. It's just a frequent pattern, this simple counting. The simple counting, actually, now, I think just, in this building, there are some Army research people coming here to visit us. One person called John, he actually chatted even the day before yesterday when we first had him meet. He said, I actually watched Ahmed did the demo. The Ahmed actually went down to Army Research Lab with me. During the lunchtime in the cafeteria, there were quite a bunch of people said, Ahmed, you are doing phrase mining, just show me what you can get. He brought his laptop at the back. He just, opened his MacBook, said, what do you want to see? So you give a document, you see what phrase you can generate. He took the Army has a manual. It's a medical manual. Okay. For Afghanistan, they have like a rescue or emergency or some typical disease. They need people, the soldiers need to read those manuals. Actually, one side is in Darcy, Afghanistan language. The other side is English. They have any page. They have two pages in the same folder. Okay, it just try the English, of course, because other people cannot understand Darcy. Okay, and he clicked the button, feed in this 200 English, more than 200 pages into his computer. 2 seconds, you generate lots of phrases. Of course, you use Linux. They start, scrolling up and down, look at the phrase quality. This is very good phrases because the medical document, in many cases, you have to get a compound words. Single one doesn't make sense. You get it, like many things are 2 or 3, they all make sense from the medical point of view. It's amazing, just 2 seconds. You generate so many. That one is before you feed into LDA, because you first do phrase mining, then you feed into LDA. Before feeding LDA, you only take 2 seconds. You generate that many. Okay, that is very fast. And that demo actually was quite eye-opening because they never expected it to be so fast, generate so high-quality phrases. So you probably see these are very good phrases you generated. And then he actually tried many things. This one was try DBRP abstracts. And first generate phrases, then feed into topics. You probably see these are very, very good ones. For example, the first one. You get a genetic algorithm optimization, solve this problem, optimal solution, evolutionary algorithm, local search space optimization algorithm, objective function. If you do optimization, you probably see this is very good. There's only one problem you can see is some are not quite phrase. Some are like a sentence, like solve this problem. Of course, you can say this is verb phrase. Because he does not do any NLP. Sometimes he does a short sentence. If they occur frequently together, he just look like a phrase. You just dig them out. Okay. There are many such things. But other than that, of course, you can feed again into part of speech, the parsing. They do this part speech tagging. You feed into that part, you can get rid of these things as well. This one is Associated Press, 1989. You probably, if you read it, if you still remember the old Bush, the George Bush, not George W. Bush, this George W.H. Bush, they still have, you look at that time, you look at this. This is the Pop John Paul, 1989. This is Gaza Strips. All these are pretty interesting phrases, right? So you probably can see what I should say is this phrase mining is very efficient and also very, very effective. Okay. Of course, that's not the whole story. The next lecture, I'm going to give you another new algorithm which use a little training and can further improve this one substantially. Okay, thank you.